In this video, I want to go over the solution to practice problem precipitation 1. This is a really important problem, and it's really vital that you understand how to solve it. So let's lay out the scenario here. We have an air mass located somewhere out here over the ocean. This is a little cross section of the Earth, and that air mass is going to move inland to the east, let's say on the Pacific coast. It's going to be deflected by a mountain range up and over this mountain range. And we want to know what's going to happen to that air mass in terms of its temperature and specific humidity by the time it reaches its destination here back at sea level on the other side of the mountain. So it's going to start here at sea level. We'll call that point A. And oops, those are too big. We start at point A, and then it's going to, there's point A, and then it's going to go over the mountain and come back and back to sea level at its final destination. This mountain range, total height of this mountain range is 1,500 meters. Okay, and the incoming air mass, the air mass at its initial position over the ocean, we're told it has a temperature of 25 degrees C, and it has a specific humidity of 15 grams per kilogram of water vapor. So let's make a little chart we're going to want to do here. So at position this is position, let's just call it position, and this is going to be the temperature in degrees C, and this is going to be the specific humidity Q in grams per kilogram of air. And so its initial position, we'll call that A. Its temperature is at, what do we say, 25 degrees C, and it's at 15 grams per kilogram of specific humidity. So let's plot that on our diagram. So 25 degrees C, 15 plots right over here. So this is our position of our initial air mass. It goes inshore, and then it starts to ascend, right? So it's going to start going up the mountain here. And as it does so, it's going to be cooling. It's going to be cooling because it's undersaturated here. It's going to be cooling initially at the adiabatic, the dry adiabatic lapse rate of 10 degrees C per kilometer, or 1 degree C per 100 meters. And it's going to continue to do that. So as it cools now, right, it's going to follow a path which takes us, the paths here in sort of blue, the path is going to take us to the left here on this diagram. That's cooling temperatures, right? And it's going to continue to go to this path. Let's label these again here. So this was our point A here, right? And it's eventually going to cool until it reaches saturation. Let's put saturation right over here, close enough. Point B, it's at, let's say this is at 20 degrees C. So it's going to cool 5 degrees as it gets to point B. All of that time as it rises up the mountain, it's just cooling adiabatically. There's no precipitation. It's cooling at the dry adiabatic lapse rate. So we can say that when it gets to point B, that's when it reaches the saturation curve. We can see from the diagram it's cooled to 20 degrees C. And again, it hasn't precipitated yet, so it's still got a specific humidity of 15 grams per kilogram of air. Once it reaches, so let's draw this point here now. So it's going to reach point B here. Let's put point B on our diagram too. So point B is somewhere like this. And remember, this corresponds to, oops, we haven't actually said that. So what elevation does that correspond to? Well, we have to use the dry adiabatic lapse rate. So it's 1 degree C per 100 meters. It's cooled 5 degrees, right? That's 5 degrees. So this must correspond to an ascent of 500 meters. And that brings us to an elevation of, we'll just write it over here, at 500 meters, right? We're at 500 meters. We've cooled 5 degrees, 10 degrees C per kilometer, 1 degree C per 100 meters. So we've reached 500 meters. We will have cooled 5 degrees, and we begin to precipitate. So from this point on, this is really important now, from this point on now to the summit, we are going to be, as it follows this path, it's going to be continuously precipitating, right? We have now reached the saturation curve. Any further ascent is going to make it cooler, and at that point it can't hold any more water vapor, so it's going to begin to precipitate, to form precipitation. So that path on our diagram though, so once it gets to B now, once it continues to ascend, it's going to have to follow this vapor pressure saturation curve like this. So as it continues to rise, it is now rising and simultaneously precipitating as it continues up the mountain. And when it finally gets to the summit, let's label the summit here, point C. So C is the highest point it's going to get to, right there at the summit. And at the summit, we have to figure out its temperature and its specific humidity. But we know how far it must have ascended, right? Because it got up to 500 meters, at the summit's at 1,500 meters. So this requires a further ascent of 1,000 meters, right? And 1,000 meters, now we're going to calculate its temperature based on the moist adiabatic lapse rate. That's 6 degrees C per kilometer, 0.6 degrees per 100 meters. And this math works out really easy because it's basically further ascending a kilometer. And so it must have cooled an additional 6 degrees C. That's the moist adiabatic lapse rate. So its temperature must be 6 degrees cooler than it was at B, so it must be 14 degrees C. So this tells us where to stop this. Actually, it tells us exactly where that air mass is going to plot on our diagram. There it is, right there at 14 degrees C. That's when it reaches the summit. So there's our summit. So it follows the path from B to C. I'm not sure why it did that. B to C, there we are, and it has reached the summit, and we know it's at 14 degrees C. We can now read off directly from the diagram what its specific humidity must be, right? At point C, it's at 14 degrees C, and 10 grams per kilogram, grams of water vapor per kilogram of air. So it's lost a fair amount of its moisture by precipitation during that path from B to C. Now, once it reaches the summit, it begins to descend. And descent involves warming. As we warm, we will move to the right on this diagram away from the saturation curve. And that always means we're going to be following the dry adiabatic lapse rate. So as we move in this direction, we are no longer precipitating. We are following the dry adiabatic lapse rate. So as it descends, it will be warming at a rate of 10 degrees C per kilometer. So we get to D. Again, we have to calculate its temperature and its specific humidity, but we know now that this is caused by descent all the way down to the bottom of 1,500 meters. And so this math, once again, is pretty easy. That's 1.5 kilometers, 1,500 meters, at a rate of 10 degrees C per kilometer. 1.5 kilometers, 10 degrees C per kilometer. Well, that turns out to be 15 degrees. So as it descends along this path, it will warm by 15 degrees. If it was 14 degrees C at the summit, that means it will be 29 degrees C when it reaches its destination. So I can plot that point up now on my diagram. We're at the same specific humidity as we were at C, but now we're at 29 degrees C. There's my final destination, D. So we are at D, so now let's go. D, 29 degrees C. We're still at 10 grams per kilogram of air, and there we go. Now, the final thing we are asked to do is to calculate the relative humidity at its final destination. So at its destination now, so let's go do this. We want the relative humidity here is going to equal its specific humidity, which we've said is 10 grams per kilogram of air, divided by the saturation level at that temperature. Now, that temperature is now 29 degrees C, so you have to actually go way up here and read what it is. It is really close to, let's just call it, for the sake of argument, close to, it's about 26 or so, 26 grams per cc, so, I'm sorry, grams per kilogram, so it's 10 divided by 26, which is 38% relative humidity. So it started off with a relative, what was the relative humidity? I think we were told to actually calculate. So when it came in at A, it had we'll do that. So at D, it had let's create it over here. So it's 38% relative humidity. Is another column over here. Relative humidity, sorry, it's messy here. But that's my relative humidity column. So it ends up at 38%. What was it initially? Well, initially it came in at 25 degrees C and 15. So back over here, so the relative humidity at the beginning would have been equal to, let's see, was it 15 grams per kilogram was the specific humidity, and saturation at that point was 20. Oh, I can do that math in my head, right? So that turns out to be 75%. So it came in at a relative humidity of 75%. It rose up over the mountains, during which time it precipitated a whole bunch of rain, and that dropped the relative humidity by the time it dropped back down to sea level to 38%. That difference reflects, of course, the rain that fell during the ascent. Also, one thing to think about, it's also warmer than it was initially. Well, where did it get that extra warmth? Well, that represents the energy added to the air mass by the precipitation event. So is losing moisture at the same time added heat, the latent heat vaporization. So, I'm sorry, evaporation. So losing moisture at the same time added heat, and that's why by the time we got back down to sea level, the air mass had a lower relative humidity but a higher temperature. It's now at 29 degrees. It started out at 25 degrees. That represents the addition of heat to the air mass caused by precipitation.